In the last 2 years, especially since the release of ChatGPT, we have seen language models become increasingly more capable on a variety of NLP tasks. For example, they can generate coherent text, which is almost indistinguishable from that of a human. They can translate accurately from one foreign language to another, and they can even write code in most of the major programming languages. However, despite these impressive abilities, we also know that LLMs suffer from certain limitations. The most well-known problem is probably that of hallucinations, which is when a model gives an incorrect answer, but in a very confident and convincing way. Another common problem is outdated or incomplete knowledge. This is because LLMs were trained on data that was collected up to a certain point in time, and so it's not possible for them to have any knowledge of more recent events which happened beyond that point. We can also mention their inability to perform tasks or actions, in the sense that a language model by itself is unable to directly access information stored in an external database. And of course, all LLMs have a maximum token limit or context window, which means that it wouldn't be possible to give an entire archive of documents as input and ask questions about it, because we would go above the token limit. Now, these are issues which cannot be solved by just increasing the size of the model with more parameters or scaling the computation power with more GPUs. Instead, there is a technique that was published a few years ago by researchers at Meta, which addresses these challenges. It's called Retrieval Augmented Generation, or RAG for short, and it works in the following way. Let's say we have an LLM and a database with documents which are either private or very recent. So in any case, these documents were not used during the training of the LLM, and it's not possible to directly ask the model any questions about the content of these documents, because it wouldn't know. The first step in the RAG process would be to query the database using a type of algorithm called semantic search. This will search for fragments of text which are semantically similar to the user question and return the top results. This is what we mean by retrieval. The idea is that if these fragments are very similar to the question, then they might also contain the answer. A common misconception sometimes is that the language model is somehow involved in the document search process, but this is actually wrong. The retrieval can be done entirely without the help of the LLM. Then, after this, we append the retrieved documents to the initial question, and we create a larger prompt which contains both the question and the potential answer. This is what we call augmentation, and it's basically a form of prompt engineering. And finally, after we have this new prompt, we provide this enhanced prompt as input to the LLM, which will generate an answer based on the retrieved information and not on its original training data. This is, in essence, how RAG allows an LLM to answer questions about topics that it hasn't seen during training. Out of all these steps, the most important one is the retrieval, because if this one is done correctly, then the rest are relatively straightforward. And in order for the retrieval to be successful, there are a few data preprocessing tasks which are usually done in advance. Specifically, we have to split the documents from the initial database into smaller pieces of text, which we call chunks. We do this because we want to be sure that in the end, the LLM will receive only the most relevant pieces of information and not entire documents which might be too large to fit in the context window. Ideally, every chunk should be self-consistent, and it should have information which is semantically related. And there are different strategies for how best to split a document. For example, we can split it into chunks of fixed equal size, or we can do the splitting based on a list of special characters. After the splitting, we use something called an embedding model to transform every chunk of text into a vector of real numbers. We do this because the algorithm for semantic search is effectively a mathematical computation that has to be done on vectors, on numerical vectors. It cannot be performed directly on plain text. The vectors are then stored and indexed into a special type of database which has been optimized for handling high-dimensional vectors. And when the user asks a question, the question doesn't have to be split because it's already small enough. So it can be directly embedded and compared with the rest of the vectors. Now, in order for the embeddings to be useful, they have to satisfy a few basic properties. And the most important one is that the geometric relationship between any two vectors should reflect the semantic relationship between the corresponding chunks of text. So this means that if two chunks of text are semantically similar, they should be embedded into vectors that are located close to each other. And on the other hand, if two vectors are far away, they should correspond to chunks which are not related. For example, in this image, we can see that some phrases that are referring to the topic of the Python snake have been embedded and grouped into vectors which are grouped in one part of the vector space. And phrases which are related to the topic of the Python programming language are clustered in a separate part of the vector space. And if the user would ask a question about one of these two topics, the question will end up in the correct group, somewhere close to the answer. So this means that we need to have a way of figuring out which elements of the vector space are the closest to the query vector. This is not an easy task because in reality, the vector space is not two-dimensional like we see here. Depending on which embedding model we're using, the vectors can have hundreds or even thousands of dimensions. So it's not possible to figure out the closest neighbor by direct visualization. Instead, we have to use a metric which can measure distances in any number of dimensions. And there are several options for this. Let's say we have two vectors, A and B. One possible choice for a similarity metric is the Euclidean distance. This is defined as the straight line distance between the two vectors. It is an intuitive metric because it depends on the distances between the corresponding coordinates on each axis. If the coordinates are close to each other, then the vectors are also close, and vice versa. Another metric is the dot product, which is given by the product between the lengths of the vectors and the cosine of the angle between them. This is a metric that depends on the orientation of the vectors. So if the vectors are pointing in the same direction, their dot product will be larger, and if they're pointing in opposite directions, then their dot product will be smaller. And probably the most popular similarity metric is the cosine similarity, which is just the cosine of the angle between the vectors. This is a metric that depends only on the angle and not on the length of the vectors. In particular, if the vectors are normalized, if their length is equal to 1, then the dot product is the same thing as the cosine similarity. The choice of the similarity metric is quite important because it can have a direct impact on the results of the semantic search. Consider the following example. We have three vectors, A, B, and C, and we would like to know which one is closer to A. Is it B or C? Well, the answer depends on which metric we're using. Because if we're using the Euclidean distance, we see that the distance from A to B is the same as the distance from A to C. But we also notice that the angle between A and C is much smaller than the angle between A and B. So if we use cosine similarity, then A is closer to C than it is to B. And it can also happen the other way around. So in this case, we see that the angle between A and B is equal to the angle between A and C. So this means that A and B have the same cosine similarity as A and C. But at the same time, we observe that the Euclidean distance from A to B is much bigger than the Euclidean distance from A to C. So in both cases, if we use one metric, the vectors are equally close to A. And if we switch to the other metric, then one vector becomes closer than the other. This is why we say that depending on which metric we're using, the notion of which vectors are the nearest neighbors can change. Then after we select a similarity metric, we can use it to find out the nearest neighbors of the query vector. The simplest approach would be the following. We just measure the distances between the query vector and all the other elements of the vector space. We sort them in order of increasing distance, and we just keep the vectors that have the smallest distance. This approach is called k-nearest neighbors, or KNN for short. It is a brute force approach because we're iterating over all the elements of the vector space. It has the advantage that it is always guaranteed to be 100% accurate, so it can be used in cases where perfect accuracy is a mandatory requirement. But it also has the disadvantage that it's very inefficient in terms of time performance. So the runtime complexity of this algorithm grows linearly with the number of vectors. So if we have a large database with millions of vectors, then KNN would not be practical because it would take too long and it would be very slow. So in this kind of cases, we can make a compromise and use a different type of algorithms called approximate nearest neighbors. These are much faster, but also less precise. They will return results from the vicinity, the neighborhood of the query vector, but not the absolute closest. They will return results which are just close enough. One example of such approximate nearest neighbor algorithm is product quantization, which works in the following way. Let's say these are the initial elements of the vector space. The first step is to partition them into subvectors, and we consider each partition to be independent from the other ones. On every partition, we apply the k-means algorithm, and we group all the subvectors into different clusters. Every cluster will have a centroid, and these centroids can be considered as approximations of the subvectors from that cluster. And then when we have a query vector, this is also partitioned, and the subvectors are, each one is assigned to one of the clusters. Specifically, they are assigned to the cluster that has the nearest centroid. So the idea would be that instead of comparing the query vector with all the with all the elements of the vector space, we are just comparing it with the centroids of the clusters, which are fewer in number. And then going back to the initial vectors, those that have subcomponents which are in the same cluster as the query vector are considered to be the nearest neighbors and will be returned by the algorithm. This is how product quantization works. There is a trade-off between precision and speed, which depends on the number of clusters, because as we increase the number of clusters, they will have fewer elements, so the precision improves, but also the algorithm will be slower because we're iterating over all the clusters. And of course, there are also other approximate nearest neighbor algorithms which are even more efficient than product quantization. Then, after the retrieval is finished, we will have a list of vectors, and we know that these vectors are associated with fragments of text that are similar to the user question. So now we want to create a prompt which combines the question with these retrieved chunks. As in the case of retrieval, there are different strategies for doing the augmentation. The most straightforward approach is called the stopping strategy. This is the name used in LangChain, in the LangChain framework. The idea is very simple. We just concatenate all the chunks retrieved from the database, and we give them to the LLM together with the answer, together with the question, and the following instruction. You use these pieces of context to answer the question at the end. If you don't know the answer, just say you don't know. Don't try to make up an answer. So this is, it's a very simple approach, but in many cases this can be good enough, and I think this is actually the default option in LangChain. Another augmentation strategy, which is a little bit more complex, is the MapReduce strategy. So this one, again, at the beginning we will have some chunks which are relevant for the question, but instead of grouping them together, we will give them to the LLM separately, one by one, together with the question and with this instruction. Use the following portion of a long document to see if any of the text is relevant to answer the question, return any relevant text verbatim. So we're asking the LLM to reduce the size of the chunk by keeping only the most important sentences and discarding everything else which is not related to the question. And after we have these reduced chunks, we do the same thing that we did previously with the stuffing strategy. We combine them, and we ask the LLM to use them for answering the initial question. This is a strategy that can be used, for example, if we have a LLM with a small token limit, or if the chunks are too large to fit in the context window. It also has the disadvantage that we're making multiple LLM calls, so the cost associated with the API might be a bit higher, and also the waiting time for the answer might be a little bit longer. And the final augmentation strategy that I want to mention is map re-rank. This one starts like the previous one. So we give each chunk to the LLM one by one, together with the question, but with a different prompt. Which is use the following pieces of context to answer the question at the end. Don't make up stuff. In addition to giving an answer, also return a score on how fully it answered the question. So for each chunk, we are asking the LLM to give us two things, a potential answer to the user question and a score of how good the answer was. And then, so for each one of these potential answers, we see which one has the highest score, and that's the one that we return to the user as the final answer. Okay, so to conclude, let's review the ways in which RAG is addressing the limitations that I mentioned at the beginning on the first slide. So the problem of outdated or incomplete knowledge is solved by the fact that the additional information is stored in an external database, and we're retrieving only what is necessary using semantic search. The inability of LLMs to perform actions is addressed by the fact that the retrieval is done by the vector database, and the top results are just given directly to the LLM inside the prompt. The issue with the limited context window is fixed by splitting documents into smaller chunks, and in case the chunks are still too large, they can be further shrinked using augmentation techniques like MapReduce. And the risk of hallucinations can be reduced by explicitly asking the model in the prompt to admit that it doesn't know if that is the case. And of course, at the moment, the topic of, there are lots of papers related to RAG that are appearing every week. I don't have time at the moment to go into more detail, so I'm going to stop here. Thank you for your attention. Yeah.
Thanks, Catalin. One idea, maybe it's so obvious that it's actually stupid, but the different, characteristics of the embedding strategies, the similarity metrics, they can, sometimes point to different results. Like by one metric, 2 documents are closer, and then by another metric, the other 2 documents are closer.
Yeah.
Have you ever thought, or is there research about combining them? And so for those cases where, say, 2 similarity metrics clash, you maybe there's, I don't know, some average score or something like that, but when 2 metrics really align, and these 2 documents are definitely the closest to the query by both of these metrics, then it's really guaranteed to be a good one. And that might maybe be a bit slower to calculate because you're calculating two metrics, but maybe crazy idea, but could you even calculate the similarity of every document to the other documents ahead of time and then just hash that and have a table so that you only ever need to retrieve the top one best document to the query, and then you can just automatically get, say, the 2 or 3 or whatever next most similar documents to that one, and then context stuff with, say, those 3 documents like that. Does that make sense? And do you know of any research on that?
I don't know any specific research about this. I mean, in theory, I think the idea might work, but the problem is that you have to decide on which metric you're using at the beginning when you are creating the vector database. So, I mean, it's not possible to just decide at the moment of retrieval to use one metric or the other. You have to decide from the beginning when you're creating when you're embedding your documents. So if you would like to do something like this, then that means from the very beginning you would have to have 2 or more separate vector databases, and you would have to retrieve documents from each one of them. So, I mean, in theory, this could work, but I don't know if, depending on how many documents, how many databases you have, it might be a bit slow.
Yeah.
That's
but
what
I just meant it's not the embedding strategy, although that's like the embedding will happen ahead of time anyway. But the actual measuring of the similarity, whether you say use the cosine or dot product or Euclidean, that would, if I'm not mistaken, that would work regardless of how they're embedded, right? Because it's just the metric. You're just, running these metrics against the vectors, and so therefore you could calculate that ahead of time as well if you wanted to. And then use a combination of and there was 2 different ideas basically. Using a combination of the similarity metrics, you don't have to do. That was just one thing I thought of to maybe tackle the problem of sometimes they give different results. But yeah.
I think it depends on exactly how the provider of the database has implemented the software, because from what I know, there are at least some vector database which force you to choose from the very beginning a similarity metric. Before, from the very beginning. So there are in some cases where you really have to choose from the beginning the similarity metric.
Yeah, fair enough. I didn't know that. Thank you very much.
Yeah.